it is my pleasure to have Jocelyn Reed and Lami Sleiman for the speaker today. And my name is Kent Yagi from University of Virginia. So let me first introduce the speakers. Jocelyn earned her PhD in 2008 from University of Wisconsin-Milwaukee, and she did 2 postdocs at AEI and also University of Mississippi. And then she joined California State University, Fullerton in 2012. And now she is a full professor at the same institute. Lami earned her PhD in 2023 from, let's see if I can get this right, Nicolas Copernicus Astronomical Center in Warsaw, and also Paris Observatory in France. And then she is currently a postdoc at California State University, Fullerton. So as most of you know, Jocelyn is one of the leaders in testing nuclear physics using gravitational waves. And there are many important works, including like constructing piecewise polytrope equation state that some of you might have used before. I checked the citation, and it has more than 700 citations as of today, so that's very impressive. Okay, and then so Jocelyn, would you like to share your screen? And
sure.
So today, they're going to tell us about proving the dense matter equation of state with gravitational wave detections of neutron stars. Okay, the floor is yours, Jocelyn.
Well, thank you very much, Kent. It's really nice to have an opportunity to talk to DGRAV, which has been sort of my home division in the APS for my whole career. And yeah, I think I saw a couple of these talks ago. There was a DGRAV without DAP talk, but this one maybe we can pitch as DGRAV with DNP, which is the Division of Nuclear Physics. And so I'm going to give sort of an introduction to why some of these nuclear physics questions are interesting to the broader scientific community. And then I think Lami is going to talk about maybe a modern evolution beyond piecewise polytropes that I'm still quite fond of to the kind of technology we'll need to explore the equation of state with current and future generations of gravitational wave observations. So with that said, the sort of founding or the basic question that we're trying to understand here is, what is the nature of matter under extreme conditions? What is the fundamental physics of quantum chromodynamics that tells you what happens at very high density neutron-rich conditions at the core of a neutron star? And because of the complexities of nuclear theory and many-body strong interactions, this is not something we have at this time a reliable access to theoretically. So we're relying on observational science to tell us what's going on at these densities. So just to give some context, this is a very common nuclear physics diagram showing a phase diagram of quantum chromodynamics. The bottom here is density, here baryon density, and 1 there is the density of an atomic nucleus. On the vertical axis here, we have temperature, going from sort of the temperatures of everyday life through the kinds of temperatures reached in heavy ion collisions, which are these tracks here, or hadronic collisions, and into the early universe. And then there's a third dimension here, which is kind of important for neutron stars, which is the asymmetry between protons and neutrons of the matter, the isospin asymmetry. And neutron stars are kind of a unique set of conditions that aren't really accessible through many of the terrestrial experiments. So we have a facility for rare isotope beams, we have heavy ion collisions and things like that, but they're primarily nuclei that are mostly equal numbers of protons and neutrons. And we need to understand other conditions to get a good picture of what's going on in the universe. So one of the roles that the dense matter equation of state plays, one of the reasons we're interested in it, is that neutron star mergers, like the Ones we can observe with gravitational wave astronomy. So the yellow there was gravitational waves that are tracked also at the bottom of this animation. They drive the merger of neutron stars, which flings out neutron-rich matter into the universe. And then the post-merger remnant, we expect in many cases to collapse after some milliseconds here into a black hole with an accretion disk. The disk is also going to produce neutrino-driven winds and potentially launch a gamma ray burst powered by the accretion disk. And so we'll have an engine of sort of a really now hot topic in astronomy for several years, a single system that can be observed in gravitational waves, optical light, gamma rays, radio, and across the electromagnetic spectrum. So to understand what's going on in those systems, you need to understand how matter behaves at the conditions we see in neutron stars. And this is also important for other fundamental questions. So one of the big questions that a lot of the broader community can really catch a hold of. This is something that actually, if I talk to high school students, they really love thinking about this. And it's how elements get made in our universe. This was an astronomy picture of the day on the top right, trying to chart the periodic table by where over the history of the universe different elements have been made. And you can see that merging neutron stars, purple, is one of the sites where we think many of the heaviest elements are forged. So this plot on the left shows a nuclear chart, a number of neutrons and number of protons, and the stable elements are in black here. And the production of these heavy elements involves reactions traveling through this diagram through many processes which take place in exploding stars, neutron star mergers, and other things that we can learn about with gravitational wave astronomy. So this is sort of why, or some of the reasons we're interested, not only for sort of the fundamental nature of matter, but also implications for understanding our place in the universe, come down to what is the dense matter equation of state. So how are we going to get a handle on this with gravitational waves? So there's sort of a few steps to this process. So we start off with some candidate neutron star equations of state. So cold, zero temperature in the sense that the temperature is not contributing to the pressure. Beta equilibrium, so all the reactions have proceeded to an equilibrium state. We have predictions for how pressure changes with density through the densities of the crust core, outer core, and central regions of stable neutron stars. So if we take this pressure density relationship, we can find, for example, the radius of different neutron stars at a given mass, and each equation of state predicts a family of neutron stars with a given mass radius curve. The other feature of the neutron star's macroscopic structure that plays a role in gravitational waves is something that can be called the tidal deformability of the star. It's related to the radius, so high pressure at the core gives us large radii, gives us high tidal deformabilities, but it's a slightly different characteristic property that comes from the distribution of mass within the star, not necessarily just the size of the outer radius. Okay, so when we generate a gravitational wave model for the in-spiral merger of two neutron stars, we model the source binary with properties of the stars, their masses, their spins, and with our current models, the additional information we need are the tidal deformabilities of the two components. Now, at a fixed mass, a larger tidal deformability will lead to a faster chirp. And the easiest combination to measure is this particular, not very beautiful combination that just comes out of the post-Newtonian theory for the leading order term in a post-Newtonian in-spiral. This is the coefficient of the term that drives the imprint of matter, a tidal interaction between the two stars that accelerates the merger by increasing the rise of frequency over time, increasing like the F dot. So this model that is plotted here is in particular one called EOB resum S. So this is not a post-Newtonian model, but it uses the same characteristic parameters that were defined from post-Newtonian theory. And one of the active work being done in the modeling community is to understand what are the relevant characteristics of the stars that imprint themselves observationally on a signal that we can measure. So in this case, there are many calibrated or higher order contributions to the dynamics of the neutron star merger, which are currently mapped to this single set of parameters, even for models we use that go beyond a perturbative framework for the interaction. So we can quantify a little bit how well or what type of modeling we need by looking at the increase in the frequency relative to a black hole as a function of frequency. These are different ways of modeling the system that come from EOB theories, so effective one-body resummations of the two-body problem, which include tidal interactions at various orders, as well as spin terms and other couplings, as well as Taylor F2, that's sort of the basic post-Newtonian expansion for gravitational wave observations, and numerically calibrated models, this IMR phenomenological model in blue, and lastly, two direct simulation results for how the frequency changes as the stars get closer together. And we have consistency in the models we use through the in-spiral and through most of the frequencies we are currently sensitive to, although the calibration of the models right now focuses on the in-spiral, so they do not currently accurately model the dynamics or the implied dynamics of the wave that is being used through to the in-spiral. So, so we need a gravitational wave model. We need a handle over the modeling uncertainty. And another direction that I'm trying not to talk too much about that I'm really interested in is how to quantify and marginalize the waveform model uncertainties. But another thing, the reason that we are interested in doing this is we want to map the size of this departure from a binary black hole model to the characteristics of the matter. So when we observe a gravitational wave, so this was the 1708-17 observation, which I'm going to use as the example of how this is done because it is still the best data we have. We see the frequency chirp from the data. We can measure things like the chirp mass because it's a driver of that changing frequency. And then we can compare the additional changing frequency from the tidal interactions through this characteristic parameter to the predictions of different equations of state. So this is how observations of gravitational waves are going to disfavor or favor models for matter that produce neutron stars of these characteristics. So the last little thing, so actually just to close that out then, the neutron star equation of state is therefore constrained by which pressure density curves are compatible with the observations we see. We can do this directly with equation of state models, or we can do it with some of Kent's work, which is using quasi-universal relations to connect the gravitational wave observations to the implications for radius, as well as to connect the two tidal deformabilities of the component stars. So methods for each of these methods are discussed here. One of the things we note, though, is if we take into account additional information, like the presence of the need to support massive stars, that changes our inferences. So additional information about the neutron star equation of state will modify the way we interpret the gravitational wave observations. So over the coming decade, we anticipate that the current sensitivities, the current observing runs 02 to 04 of the gravitational wave observatories will lead to upgrades at the end of this decade through to 05, into the coming decade of A sharp, and potentially the commissioning and building of next generation facilities in the later 2030s, like Cosmic Explorer and Einstein Telescope. And as we reached to higher and higher capabilities of the interferometers, we are going to see further into the universe. And for a given signal, this little triangle is 170817, if we saw it in a next generation facility, the signal to noise ratio for Cosmic Explorer would exceed 1,000. So the same signal in a next generation facility will allow really high precision measurements. The detector noise versus the waveform model differences leads to a comparison that says a lot of matter physics can be extracted by interpreting the imprint on the waveform that we'll be able to measure. So this is where I'll close out here, because one of the key questions that this leaves us with is, how are we going to do the best science with these next generation observations? And in particular, what kind of equation of state framework are you going to need to be able to explore the kind of sensitive observations that we're going to look at? And so that's where I'm going to turn things over to Lami to tell you about some of the work we're doing and that she's leading to answer these questions. I will stop sharing.
Thank you very much, Jocelyn. Now, Lami, if you can share your screen and take over, that would be great.
Can you see my screen now?
Yes.
Okay, perfect. So thank you very much, Jocelyn, for the introduction. So I'm going to talk to you about a paper that we actually wrote together with Jocelyn and was published in Physical Review D a few months ago. And I'm going to discuss the use of quasi-universal relations in the context of next generation detectors. So in order to talk about quasi-universal relations, I first need to do a little bit of a detour on neutron star equations of state, and particularly on a few different equations of state sets that we're going to use for the quasi-universal relation study. That will be a good occasion for me to mention a work on semi-agnostic model, which will be needed in the context of next generation for equation of state inference. So there's different ways that you can construct an equation of state model. You can do it the nuclear physicist way or the astrophysicist way. If you want to build a nuclear physics-based model, you're going to have to choose a theory of strong interaction. So let's say you are a nuclear physicist who likes relativistic mean field theory, and you're going to build a Lagrangian density for all the particles in play in your neutron stars. So for example, for nucleons, but also for some mesons that could be mediating the strong interaction between nucleons. If you are, of course, you can use something else than relativistic mean field theory. You could also use theories that are non-relativistic based on energy density functionals from the Skyrm force or the Cogney force. So your theory of strong interaction will be written in terms of some coupling constant or some parameters that you can also fit to nuclear laboratory experiments. Now, if you are using relativistic mean field theory, for example, from this Lagrangian density, you will have to make some approximations and then build the equations of Euler-Lagrange. And then with those, you will be able to write and compute an equation of state. But this process is quite long and tedious. So if you want to use astrophysical information to inform on the equation of state model that you have just made, you can do that each one by one, and you can test the validity of your model of strong interaction with astrophysical information. So here is an example for three nuclear physics-based equation of state model. The names don't really matter, but two of them are based on relativistic mean field and one is based on Skyrm theory. You have here represented the tidal deformability of your neutron star, as Jocelyn has introduced, to be the propensity of your neutron star to be deformed by the gravitational field of a neighboring compact object. And you have in the x-axis the mass, the total mass of your neutron star. So if you were to observe, let's say, the mass and tidal deformability from gravitational wave detection and it could draw a contour which could look, look like this, then you would be able to eliminate this third equation of state as being unfit to astrophysical data. Now that's the nuclear physics people way of doing this. Astrophysical people are more fond of what I would call agnostic models. The idea is to construct not equation of state one by one, but to construct a ton of equation of state which will be used for Bayesian analysis. So you won't follow a strict theory of strong interaction. You will follow basic thermodynamic consistency, and you will use a model that allows you to generate equations of state fast and allows you to create a large number of equations of state that can explore the plane of pressure and energy density in a very complete way. Then when you're going to use astrophysical measurements to inform on the equation of state, you will use your equation of state prior based on, which is made of maybe tens of thousands of equations of state. And you will use the Bayesian analysis to be able to build an equation of state posterior. And this posterior will be as tight as the sensitivity of the detector permits. So among the agnostic models that we have quite a few in the literature which are based on parametric approaches. So the famous ones from Jocelyn, the piecewise polytropes. There's also the spectral representation, which is right now used by the LIGO-Virgo-Cagra collaboration in the study of neutron star gravitational wave detection. There's also the sound speed approach. And there is also another family of agnostic models, which we would call non-parametric. So this idea of saying non-parametric is just that the parametrization is not done directly on the equation of state. There are still some parameters, but they are not directly on the equation of state. One very famous model would be the Gaussian process approach. And in the rest of the talk, I will use the Gaussian process publicly available set. And this Gaussian process is also informed by astrophysical measurements of heavy pulsars made in radio, mass measurement of heavy pulsars made in radio. It's also informed by gravitational wave event GW170817 and by NISO detections, which measure the mass and the radius of the neutron star. Okay, excuse me, I need to remove this bar. I don't know how to do that. Sorry. Now, you can try to find a compromise between those two approaches, the nuclear physics types of equations of state model and the agnostic sets. And this is what we did with some colleagues from France, from Caen and from Paris and Strasbourg in a paper we published this year. The idea is that we build semi-agnostic models. We wanted to incorporate nuclear experiment information as well as nuclear theory constraints onto an agnostic set of equations of state. So at low density, what we use is the meta-modeling approach, which represents the energy density as a function of the baryon density in terms of microphysics parameters, which can be informed by nuclear experiments. We also constrain our low density equation of state by chiral effective field theory, so by nuclear theory. And at high density, we keep things completely agnostic and use piecewise polytropes. That's another set of equations of state that I will use later in this talk. The second set, aside from the Gaussian process set, will be the meta-model set. So if you see this here, it's based on a meta-modeling approach, which is a semi-agnostic model. And those types of model bring the best of the two worlds. You have nuclear information, but you also have something agnostic and sufficiently agnostic to represent the variability of the core equation of state, given that we know very little on the neutron star core equation of state. So again, here is the tidal deformability as a function of the mass. The three equations of state based on nuclear models are represented again. And in blue, you have the GP, the Gaussian process, informed by astrophysical measurement. This set is actually comprised of 10,000 equations of state, and the meta-model set is in green and comprised of 50,000. Okay. Now let me talk about quasi-universal relations and exactly what they are. So, as Jocelyn has mentioned, macroscopic parameters of neutron star, they depend on the equation of state. That's basically at the heart of the whole idea behind dense matter inference. That's because mass and tidal deformability depend on the equation of state, that you can use measurements of those two quantities to infer knowledge on the equation of state of dense matter. So here again is the tidal deformability as a function of the mass for the two sets that I've just mentioned earlier. And the relative difference for the tidal deformability is of the order of a few up to, let's say, 10. However, there exists in the literature, some relations between some of the macroscopic parameters of neutron stars that seem to be almost equation of state independent. This is what we call the quasi-universal relations. And here is one represented here. You have the tidal deformability, this time as a function of the normalized moment of inertia. So it's just the moment of inertia times some constant divided by the mass to the power 3. And in this case, the relative difference on the tidal deformability is only of a few percent. And I'm using exactly the same set that I've just talked about earlier. Now, not all of the quasi-universal relations that are discussed in the literature are equal in their universality. This relation between tidal and normalized moment of inertia is very, very universal. So it depends very little on the equation of state. But here is another reported quasi-universal relation, this time between the tidal deformability and the compactness of the neutron star. The compactness is just the mass divided by the radius times some constants here and there. And here the relative difference on the tidal deformability is of the order of let's say 10%, a little bit less. I have another one, which this case relates the normalized moment of inertia and the compactness. And in that case, the relative difference in the moment of inertia is of about 20%. So we don't really have a very strong criteria, let's say a relative difference number for a quasi-universal relation to be considered universal. With regards to the underlying physical meaning of why we have quasi-universal relation, I'm not going to get into the details of that. There is no very definitive answer. There's very nice hypothesis, mostly discussed by also Kent Yagi, so he will be able to inform on this much better than I can. I'm going to focus more on what they are used for. So on one hand, you could use quasi-universal relation to test the theory of gravitation, because if you believe that your macroscopic parameters, or at least a certain relation, doesn't depend on the neutron star interior, then the only degree of freedom left would be the theory of gravitation. So it's a good way to test general relativity. But another way to use quasi-universal relation, and that's what I'm going to focus on, is parameter extraction. So let's say you have a gravitational wave measurement from a double neutron star binary merger. And from that, the collaboration from the gravitational wave detector give us a contour for the mass and tidal deformability. So a measurement of the mass and tidal deformability. Now, if the relation between tidal deformability and compactness is supposedly independent of the equation of state, I'm going to be able to use my tidal deformability and my mass to get at the radius. This is what has been done by the LIGO-Virgo-Cagra collaboration, which I think at that time was just the LIGO-Virgo collaboration in 2008, using data from GW170817 to extract the radius. Similarly, you can use another quasi-universal relation to extract the moment of inertia. That was done by Landry and Kumar in 2018, also with GW170817. Now, in practice, we make feats of those so-called quasi-universal relations, and we claim a certain precision on the feat, which corresponds to the difference between the feat line and the edges of the distribution of points for this relation, given a certain equation of state set. So there are many fits discussed in the literature. For example, here I'm representing this line, and this is a feat taken by the paper of Yagi and Younes 2017. There are many feats available in the literature. Now you can clearly see, however, that the equation of state variability, which basically is the feat precision that is given in the literature along the feat parameters, the equation of state variability depends on the set of equations of state used to be able to build this quasi-universal relation. So for example, here, the equation of state variability for the meta-model set is much smaller than the equation of state variability based on the Gaussian process set. Now I'm going to talk about quasi-universal relation in the context of detector sensitivity. So the next generation of gravitational wave detectors are going to give us very tight contours for the mass and the tidal deformability. Now here is a simulation that I've made with the Bilby software. The idea is that I'm simulating a double neutron star binary merger. I took the luminosity distance and the sky localization of GW 170817, but I used the sensitivity of Cosmic Explorer, which is one of the next generation facilities that we hope will be built. Excuse me. Now you can see that the error and the contours on the masses are going to be very tight. We have here about 0.05 solar mass variability in the contour. And with regards to the tidal deformability here, we can have, in this case, we have about a 10% error on the measurements, but we can even go to higher precision than that when we consider higher mass types of double neutron star binary mergers. So the next generation will give us very tight contours for the mass and the tidal deformability. Here are those contours. Actually, there's the contour that I've just shown you, plus another one for higher masses types of neutron stars in the binary merger. This is superposed to the different equations of state and equations of state set that I've discussed earlier. And you can see that the contours are much, much smaller and can distinguish between the three nuclear equation of state based model that I've talked about earlier. Now, parameter extraction with quasi-universal relation, it will work if you can neglect the equation of state variability. And you can neglect the equation of state variability if your detector precision permits it. So with Jocelyn, we asked ourselves a few questions which we wanted to answer. So the first one was to say, what if the fits that are claimed that are written in the literature claim a certain precision that underestimates the equation of state variability? This is something that I actually worked on with colleagues from Poland a few years ago in two papers that were published in Physical Review. So to be able to be entirely sure of our equation of state variability, what we did is that we used our agnostic and our semi-agnostic set of equations of state and we made some fits. For example, we did so for the relation between the compactness and the tidal deformability. The idea is that the fit functional looks like this, and this AK here corresponds to the different fit parameters that are represented here. We did this fit of this relation for all the different sets that we have, including the Gaussian process and the meta-model sets. So it's not important that you take a look at the parameters at all. What's more important is that, of course, with those fits, we also reported a certain precision of the fit that correspond to the equation of state variability of the relation. Now, for the relation between the compactness and the tidal deformability, you can go as high as 12%. And the fit precision is always much worse for the Gaussian process set than our meta-model set. And we also did it for the relation between the normalized moment of inertia and the tidal deformability. And in this case, we have a variability of the equation of state, which is much, much lower, about sub%. Now, the second question we asked was, what if the detection we have is so precise that the equation of state variability of the quasi-universal relation becomes the first source of uncertainty? So to answer that question, what we did was parameter extraction with two types of sensitivity. We used O4 sensitivity, which is the fourth run, the projected sensitivity of the fourth run of the LIGO Virgo Cagra facilities. So basically the sensitivity we're having right now. And we also did this parameter extraction with the sensitivity we will have with Cosmic Explorer and Einstein telescope. Now here is a representation of the mass as a function of the radius. So we are doing radius extraction from measurements of the mass and tidal deformability using the quasi-universal relation fits we made on the compactness and tidal deformability relation. In orange, you have the contours for the radius. In the case of O4 sensitivity, and in teal, you have the contours for Cosmic Explorer and Einstein telescopes, so the next generation of gravitational wave detectors. Those plain lines corresponds to the parameter extraction if you only use the fit. So in this case, we just wanted an example of what happens if you use only the fit line and you do not include at all the equation of state variability. Now, those dashed lines corresponds to the parameter extraction with the inclusion of the equation of state variability of the fit, using the same approach that was taken in Abbott et al. 2018 when they estimated the radius of GW 170817. Now, for O4 sensitivity, the parameter extraction, whether you include the equation of state variability or not, doesn't matter. The reason why is because the sensitivity of O4 is sufficiently poor that it is the first source of uncertainty. In the case of Cosmic Explorer and Einstein telescope, that is no longer the case. This plain line here corresponds, is somehow a visual of the sensitivity of the detector directly. And we see that in this case, when you include the equation of state variability, which you should, the lines are much, much larger in the radius. So I didn't mention that, but that was done with the fit based on the meta-modeling approach. If you do that with the fit based on the Gaussian process sets, you even have for O4 sensitivity a little bit of variation, even though we can consider it reasonable. And finally, the third question we asked ourselves was, what if the way we include the variability of the equation of state in our parameter extraction is unjustified? So in the 2008 paper from the LIGO-Virgo-Kagura collaboration on the radius extraction from GW 170817 data, the way they do this to include the equation of state variability is that they're going to assume a distribution around the fit line, which is peaked on the fit line and away from the fit line looks like a Gaussian. So we took a look at the distribution of points for our two sets of equations of state. In the first case for the compactness at different values of the tidal deformability. And the distribution of point really is not necessarily looking like a Gaussian distribution peaked on the fit. We did the same thing for the moment of inertia, so the normalized moment of inertia for different values of the compactness, and the conclusions are the same. So what we did was to test this Gaussian hypothesis of the fit equation of state variability inclusion. We compared the Gaussian approach done for GW 170817 in the paper of 2019 to using not a Gaussian distribution, but a uniform distribution. This is those dotted points, which in the case of Cosmic Explorer and Einstein telescope gives even much larger radius contours. And finally, for good measure, what we did is that we didn't think that there was any sort of distribution around the fit line, but we took the fit limits. So we did plus or minus the fit error, basically. And this is those field areas in here. And the conclusion is the same in the case of Cosmic Explorer and Einstein telescope. So all the figures that I've shown you are how to extract measurement of radius from mass and tidal deformability, but you can also make a measurement of or extract the moment of inertia from the measurement of tidal deformability and mass using, in this case, a quasi-universal relation fit of the relation between normalized moment of inertia I bar and tidal deformability. I've shown you that earlier. This relation is particularly it's a particularly universal relation. I mean, the equation of state variability is about a few percent, even sub-percent. In this case, the extraction of the moment of inertia with quasi-universal relation does very, very well, even in the case of Cosmic Explorer and Einstein telescope, simply because the universal relation used is very, very universal. So it will be reasonable for Cosmic Explorer and Einstein telescope to use quasi-universal relation to extract the moment of inertia, but however, to extract the radius, it will not be. And finally, the last thing that we did was that we compared the extraction of the parameters either using the quasi-universal relation or using direct equation of state inference. Now, if you receive a signal on the mass, a gravitational wave signal, and therefore you can extract contours for the mass and the tidal deformability, you can use a Bayesian analysis to do some equation of state inference. You will get an equation of state posterior, which tells you which equations of state are in accordance with your astrophysical measurement. If you have equations of state that are in accordance with the astrophysical measurement, for each masses of your distribution of points in mass from the gravitational wave measurement, you can take a look at the corresponding radius or moment of inertia. In that way, you would be able to extract a measurement of the radius, not using a quasi-universal relation, but directly with equation of state inference. So this is exactly what we did. We compared radius and moment of inertia extraction either with quasi-universal relation or with direct equation of state inference. So here, in this case, you have the moment of inertia distribution. The plane line corresponds to the extraction of the moment of inertia directly, no, not directly, sorry, with quasi-universal relation, and the field areas correspond to the extraction directly with equation of state inference. We use the same color code for the Gaussian process set and the metamodal set. Basically, the two approaches are pretty much equivalent. This is again related to the fact that when you extract the moment of inertia with quasi-universal relation, you use a quasi-universal relation, which is very, very universal and has very little equation of state variability. We do see a little bit of a difference between the direct inference either with the metamodeling sets or with the Gaussian process set. That comes from the fact that equation of state inference depends a lot on your equation of state prior. And my metamodeling approach is a little bit in favor of quite a stiff equation of state model, which leads to quite high moment of inertia. Now, in the case of the extraction of the radius, we did the same thing. And in that case, the conclusions are really different. We see a clear difference between extracting the radius either with quasi-universal relation or with equation of state inference directly. With equation of state inference directly, we have much more peaks distribution, so tighter contours for the radius. So in the context of the next generation of detectors, in this case, extracting the radius with equation of state inference directly will be much better. Now, you could tell me, well, you can just redo your fits, right? You can just say, we have new measurements. Why not do equation of state inference, get a new posterior set of equations of state, and use that to remake a quasi-universal relation fits? That's absolutely possible, but that's defeat a little bit the purpose of quasi-universal relations, simply because you're going to have to do an equation of state inference. So in the end, doing direct equation of state inference makes more sense and is a lot less tedious. So I'm going to conclude here. So gravitational wave detections from neutron star involved mergers can inform on the behavior of neutron-rich and dense matter beyond anything that can be achieved not only by nuclear experiment, but also by nuclear theory. The next generation of gravitational wave detectors, which will be the Cosmic Explorer project for the USA and the Einstein Telescope project for Europe, are going to provide us with more sources, a ton more sources, but also with detections with increased precision. Quasi-universal relations can be used to extract a measure of the radius and the moment of inertia from gravitational wave detections of the mass and tidal deformabilities of neutron stars. And the next generation of gravitational wave detectors will be so precise that quasi-universal relation equation of state variability is going to be the first source of uncertainty in radius extraction, and we will prefer going towards equation of state inference directly. I thank you for your attention, and if you have any questions, please go ahead.
Thank you very much, Jocelyn and Lamy, for your wonderful presentations. Now it's time for questions. So if you have any questions, please raise your virtual hand, or you can write your questions on the chat. And while we wait, let me ask one question. So in the analysis, you considered mainly two different equation state types. One is GP plus Astro, the other one was MN plus Chi plus Pulsar. So based on these legends, I guess that you impose different Astro constraints because one said Astro, the other one specifically said Pulsar.
Absolutely.
So,
I'm really sorry, I forgot to mention that. Okay, the Gaussian process set, I'm taking from the publicly available on Zenodo set from Isaac Legrand and Philippe Landry and Reed Essek. It's Gaussian process informed by GW, so gravitational wave, NICER, and pulsar measurements of heavy neutron stars. The meta model is constrained by Carroll effective field theory. This is the Chi, and the PSR is, yes, heavy pulsar measurements of from radio types of data. So in the meta model, you don't have the gravitational wave information, which is one of the reasons why the meta model likes stiff equation of state model a little bit more.
And any reason why you didn't include those NICER and GW constraints?
No, because in the other paper we made, actually, I used gravitational waves, and in the paper we present sets which are only constrained either by PSR, but also PSR plus GW and PSR plus GW plus NICER. Probably I can do exactly the same thing, of course, with GW information. In this case, I have not, unfortunately.
Okay, yeah. I was just wondering.
At least in the figures. But we can absolutely impose any type of astrophysics in constraints on the meta modeling approach.
Okay, and you, can you unmute yourself and ask your questions?
Oh yeah, I want to ask two things. I think that this question can be redundant. I mean, duplicated with the formal question, but I want to ask it once more. So I want to ask about GP because I also using that one, and what data set did you use for GP on that, and what kind of framework was used in there?
So in the Gaussian process set that I'm using is the publicly available one, which was made by Caltech person Isaac Legrand, Philippe Landry, and Reed Essek. So there is a Zenodo repository publicly available where they have, actually, I think they have 3 sets publicly available, one which is informed by pulsar measurements only, one pulsar and gravitational waves only, and one with everything, which is pulsar, GW, and NICER detections. So that's the one that I'm using. They're publicly available. I did not redo them entirely.
Okay, got it. And then there's a second question. I'm just heard about tidal deformation because I'm new for here. So, but I want to know why they are important and how can we figure out the tidal deformation from neutron star equation of states.
So, and Justin, of course, you can intervene at any moment. So from the point of view of the neutron star, basically this tidal deformability is how much the star is deformed by the presence of another compact object and the presence of a gravitational field nearby, right? However, this response in deformation depends on the matter inside of the neutron star. So if you have an equation of state, you're going to use the Tolman-Oppenheimer-Volkoff equations that solve the mass and the radius, as well as what we call the K2 love number equations, which really those love number are related to the quadrupole moment deformation. And from an equation of state plus those equations in GR, you will be able to get a tidal deformability. So the way we do things is that an equation of state model corresponds to a relation between mass and tidal deformability modelized by those equations in GR. And on the other hand, we have detections of the mass and the tidal deformability directly from gravitational wave detections, because the tidal deformability wow, I lost the word. Imposes, yeah. It imposes a certain form of the waveform, basically. There is an imprint. There is an imprint, a direct imprint of the tidal deformability onto the gravitational wave.
And
so go ahead.
I just wanted to add that there are some additional quasi-universal relations implied, because the tidal deformation parameter we use is a perturbatively defined quantity for an isolated neutron star. But then when we compute the impact that a given equation of state would have on the waveform, we consider higher order deformations and other effective modifications of the waveform that are mapped to the perturbative tidal deformability parameter, but is not the only term that we use to modify the waveforms.
So if I just construct the equation of states as a baryon density and the energy per particle, then we cannot know about the tidal deformation constants from that, but we need to add some perturbation on that.
Yes, you can calculate it with a 2-0 mode perturbation.
So external work is needed, not only from the equation of state then.
It's not so different from calculating like the mass and radius of a given central density. It's just a couple additional equations.
And if I have a derivative information of equation of states, then I can derive the tidal deformation constant also?
Yes, so an equation of state will give you relations between mass, radius, and tidal deformability. So from an equation of state, you can model that using some equations, which are Tolman, Oppenheimer, Volkov, and K2-Love number.
Yeah, okay, got it. Thank you.
If you want to take a look at those equations, the paper from Tanya Hinderer from 2007 is pretty nice for the K2-Love number.
Tanya and
Hinderer.
who?
Hinderer, Hinderer, and I think it's 2007, but Jocelyn knows better than I do.
Oh, yeah, I've got it. Tidal love numbers of neutron stars, you mean?
Mm-hmm.
Okay, got it. Thank you.
Okay, I don't see any hands up or any more questions, so I think we can end here. So let me thank Jocelyn and Lami again for their great presentations. And let's see. So we will make an announcement for the December seminar once we have the details available. And then let me remind all of you that we are accepting nominations for the future speakers, including self-nominations. And if you have those nominations, please let us know via Google Forms that I just sent the link to the chat. And you can also find the link in the email for this seminar's announcement that was sent on October 21st. Okay, then I think that's it for today. So thank you all for joining today, and I hope to see you again in December. Thank you very much. Bye.